right.
Break its axle or...
Yeah, a lot of stuff going around. So one of the things, a lot of things in here are like, oh, that makes sense. I can relate to that. And here's another one of those things. I think we talked about this. Didn't we? Yeah. Okay, the whole clouds can do both. They can actually have a cooling effect during the daytime, but clouds will have a warming effect at night. But now kind of in the sense of talking about ranges, we're going to kind of revisit that. So here's my diagram. I remember because my moon looked like a banana. Okay, here's the Earth's surface. Okay, and here's the sun. Okay, and here's clouds. And have you never, gosh, not just a cloud, but I tell you, the gypsum plant, like you're coming down 61 this way, if there's a big old thing of vapor going up, a cloud of vapor, it should be a cloud of liquid, condensed vapor, but when you travel through that, the temperature drops in your car. It just does. Okay, so cooling effect.
Now,
okay.
I have a question that's old school stuff that I'm trying to remember. And it said, you know, on a cloudy day, you get more sunburn than you do on a normal day.
Really? I'd have to look into that. That's interesting.
Because that has to do something to the albedo, the reflection of the clouds.
I don't know. I'd have to think about it. I don't have a good answer for that right now.
Put sunblock on.
It's interesting.
Yeah,
why is it colder on in winter? Why is it colder when there's no cloud in the sky than when there is clouds in the sky?
I don't know. We'll have to. Maybe this will help answer that. Because like at nighttime, and actually the reason we have any temperature we have has to do with the time of year, the tilt and all that, but it also has to do with air masses that are coming and going. So it's probably might be one of those. So here's the deal. At nighttime, what's these red lines? We'll be talking more about that. The radiation from the Earth. Yeah. Okay. So here's where, here's where actually at nighttime it makes a warming effect. So on this, here's a figure. Okay, we have a red line and we have a blue line. And actually, this is not a climatogram like we talked about on Wednesday. This is actually just a 24-hour cycle. Yep, a daily cycle. So I'm going to ask you which one do you think, and along the y-axis is temperature. Okay, so here we have the temperature getting high during the day, temperature getting low at night. So how many people think the red line is without clouds? That would be correct. Does that make sense? Yeah. And the blue line is clouds, both during the day and at night. So when it's overcast during the daytime, your temperatures are not as hot as they would have been. And when it's overcast at night, your temperatures are not as cold as they would have been.
So then, if you have a clear day that's sunny and a cloudy night, you would have the least
That's right.
temperature?
Yeah, if you're after the heat, if you're making the most heat for your if you want the most heat possible, you want to have clear skies when the sun's out, and you want the clouds to roll in at night.
And it would also keep your range
to retain.
Yeah.
I don't know about range. I'd have to look at that, but
if the day got warmer,
yeah,
and then the
it kind of
maybe
depends.
it wouldn't go down as much.
But clearly, you mentioned range. Clearly, you can see that the range that we talked about on Wednesday. You know, our range for clouds is definitely less than the range for clear days.
Mm-hmm.
The swing, we call this the swing, is a lot greater. Actually, I do think that's a test question. Swing is a lot greater for clear days. It's a lot clearer for clear days, but I'm not going to mix the bag of it's either all clear or all cloudy.
It's just one of the chapter 3 questions.
So this is back to the climatograms. Of course, the J stands for this one. Yep, there's 4 J's. Okay, June and July. So this is the year, okay? And what your author's done is to pick a location. I need to double check that I'm thinking this might be a monsoon effect, but pick a location where at certain times of the year, these bars represent precipitation. So basically they're saying this location, which is in the northern hemisphere, so you would expect it to experience summer the same time we experience summer. But instead of being hot, look at what it is in June and July. It's not. And the reason is because it's got all this precipitation. well, that's not it. So that is it. But what else does it have with the precipitation? Precipitation's falling from clouds. So it's titled Chronic Cloud Cover for a series of time, a period of time. And definitely it has a cooling, overall cooling effect. Okay. So that's that. I think it was a neat example. Okay. So we're going to see a few maps of the world. Okay. And one of the neat things we're going to talk about later is the hotspot. I'm going to grab the globe. So intuitively, you would tell me that the hotspot is where? Equator, right. Okay. And I love this phrase, actually. I'm going to use the phrase later that the hotspot wanders. Actually, the hotspot wanders. And that's not too much, but a little bit. It's the wandering hotspot. And actually, that hotspot is called the Intertropical Convergence Zone, ITCZ. Isn't that wonderful? Anyway, that's the hotspot. Yeah, and I'll put it on the next slide. So not so surprising that it wanders. And you're going to see in a minute the 6 months apart where the hotspot is. But the other things I want you to notice on this map are kind of what we talked about with regard to, what'd you guys tell me, North America. Which coast are you going to go to for warm water?
East.
Yes, okay. We talked about that. And actually, in the Northern Hemisphere, we have clockwise. This is kind of hard to do. Yeah. Clockwise motion. Okay. Relocating warm water to the poles. But look for that on this next slide, too. And also, we said that ocean gyrate. That's right. Kind of different currents stitched together to make the ocean gyrate. Also, we talked about how the oceans are stubborn to heat up and cool down. Okay, so look for that. So here's January. So these are the average temperatures for that month, for those locations, about climate, using climate data. Okay, and you can see the hot spot. See, January we're having winter. Okay, so we're kind of looking for the hot spot down here. I'll go ahead and throw up that acronym for the hot spot. I just think it's pretty. Okay, I know. So it's a little bit south of the equator. You might not be able to see it, but that actually is 0. That white line is 0 latitude. So it's a little south. Yep, and actually, I really probably should draw it more wandering because it does wander more than that. Kind of wanders, maybe kind of dips down here.
It oscillates,
Okay.
doesn't it?
Yeah, we're going to see 6 months later it moves north of the equator. So we generally call that the ITCZ, Intertropical Convergence Zone. Okay.
I don't think it has a heart in it.
It could.
It does now.
It does now. So
Oh, crap.
notice that, and I don't know if this is a typo. I left it up here. Actually, this is July. Yeah. It says what? July there?
Yeah, it says July here, but yeah, I
Yeah.
saw February. I was like, whoa.
Yep, so July. So find the hot spot. And it has migrated north. So when you talk about oscillating, it does go back and forth throughout the year.
If the hotspot isolates, what happened? Where was the hotspot most likely located during England and Ireland's mini ice age?
I don't know. That's a different subject. We'd have to go back. This is climate data, so
Or what did it
no, that would probably be a year anomaly. So that's not a climate. That's not a averages. Okay. So, all right. Now the other thing I said to try to see if you can you catch any difference on our coast that I mentioned? All right, so here we go. Here's North America. Let's see. Does it look a little warmer in the Atlantic than the Pacific? Yeah, I'll buy that. Let's pick on the summertime. Yeah. That is interesting. Look at this kind of dipping down, or the cold water coming from the poles towards the equator here. This ocean,
I
right?
noticed by California, it stays between 60 and 70 degrees.
Yeah, good place to move.
Yeah.
I agree.
California's gonna fall off.
So this one's a little different, and again, this goes back to one of the things that we kind of emphasized on Wednesday, the idea of throughout the year, we talk about these swings. And we have different swings depending upon kind of our location. We said that if you are in Iowa, you're not near an ocean, right? The biggest thing you got going for you is the Mississippi, right? Okay, we said that actually we're kind of at the mercy of, we have large swings, okay? Coasts, not so much. So actually that's, yeah, exactly, the ocean water does that. So these are not temperatures per se, they're the swings. So check out the swing in our neck of the woods, 50 degrees Fahrenheit or so, okay? That's like between the coldest day and the coldest day and the hottest day of the year. Okay, but look like what if you're, and these are surface temperatures. Look like the closer to the poles you get, what happens to the swings?
It gets hotter.
It gets,
colder.
the swings get larger. Yeah, they're just crazy, the difference. You're like, dude, can you not decide?
Make up your mind.
What about the equator? What kind of swing do we have there? Yeah, it's like, oh.
Differentials between two degrees.
Yeah. So remember, in the equator we have a lot of water, and water tends to keep its heat or keep its coolness. Water does that. It moderates the temperatures. But the other thing about the equator is if you were to look at the sun kind of, the hot spot of the sun migrating this way and migrating this way in January, migrating this way in July, basically if you're at the equator, you're kind of constant with regard to solar radiation. So that's kind of nice. All right. Too many R's, rotation, revolution. So this is talking about the Earth spinning on its axis, rotation, right? So we talked back in chapter 1. Remember, I stood here and I kind of talked about the sun rising in the east and setting in the west. Okay, so we have the angle thing going on. And the biggest angle we can get with the sun would be 90. Actually, that really doesn't happen too much for us here. But when it's rising, there's a small angle. It gets bigger, okay, and then it sets. Okay, so with the small angle has consequences. We talked about beam spreading. Actually, that's on your, and beam dilution, because it kind of has more of the atmosphere to go through. So every day we have this effect, and we're going to kind of take a look at this. The hottest time of the day. When is the hottest time of the day?
No, not 2.
Like what? 2, 3, 4 o'clock? Yeah, 2 to 4-ish. Yeah. At noon is when the most direct rays are falling on the sun, but actually it's falling on the earth from the sun. But actually, it's not until there's a delay when it's the hottest temperatures. So we'll talk about that in a minute.
Like I said, I always thought it was like noon and 1 o'clock.
Yep. Nope. It's about 2 to 3, 2 to 4. I don't know. It's called the lag of maximum. We're talking about kind of the delay, the lag of the maximum temperature
You
from
best
when
don't
it's
go off running.
Yeah,
Worth a sweat.
that's true.
I just
So-
did to Ohio during 2 days.
So this is an assortment of days. You see the 19th, the 20th, the 21st, 22nd. So I'm going to show you at the end of this basically how they got this. But what they did is basically have a piece of paper that's on a drum, and the drum rotates, and the little pen goes up and down to say what the temperature is. So it's kind of nice. It's kind of automatic. But if we were to kind of look at where the peaks are, we would find that they are delayed after noon. And you kind of have to look at what, like this is noon, this is what, 4 o'clock, yep. So in between there is about 2, yep. So this one was earlier, this one was about noon, this one's about 2. This, like the slide says, actually here, and this is kind of one of the things that you brought up, I said that what the temperature is like kind of depends upon not only the sun, but this is talking about an air mass moving into the area. And we'll talk more about those later. We have no control over it. Okay, so that kind of delay to when the sun is highest, it's at noon. Okay, but the hottest temperatures are delayed, and I have a figure to kind of to show why that is from your textbook. Okay, that's called lag of maximum. But do you think you can get a heck of a sunburn at noon?
Yeah.
Yeah. So you would think getting a sunburn or suntan, that's when you're going to go with your angle. So you could even do it 11. Yeah. I think 11's the best time if you want to take it.
I
Yeah.
think,
So, say you're swimming in like a boat, would the sun kind of, and the water kind of help the process for the sunburn or no?
Yeah, the water
Right.
reflects the sun.
Yeah.
That's the magnification of water.
Yeah, that it's reflecting. It would provide a reflective surface. So yeah, I think that would definitely help you burn.
Be due to the noon sun rays heating the Earth's top layer crust.
I don't know. Could be.
Causing water in the actual crust to heat over time. Causing
Could be.
humidity.
I don't know. We'll talk more about humidity in Chapter 4. So that's coming up. On Monday we'll get to Chapter 4. So this term is on there. So here's the figure from your textbook. And the yellow is basically the insolation. I don't know if you guys remember, but I said insolation is that energy that the sun is sending us. So you can kind of see because of the angle, we have the lowest amount of insolation at sunrise. Okay, it peaks at noon. Okay, just like James was saying, and it kind of peters off. So the red thing is the red thing is basically the Earth re-radiating energy. Okay. And honestly, when it comes time for us to feeling cold or warm or whatever, our surface temperatures are much driven by this. Okay. So you see that peak is delayed, and so actually that's when you think we will generally see our warmest temperatures, as long as we don't have some sort of air mass coming through, advecting through. I can.
You go back one, okay. I missed two.
This one?
One more. That one.
I didn't see that part.
I didn't have it very long. I don't know where my blanks are sometimes. So, like this class, a lot of it's like, that makes sense, or I've experienced that. So definitely go with that. But now you know a word to put with it. And on your test, that's kind of what I'm after. Kind of can you connect with kind of the terminology a little
I
bit.
used to call your lag a maximum hell.
So this is kind of, the blue line is kind of what we saw on the several days, okay? Kind of the maximum temperature. All right. So yeah, we'll be talking more about humidity and frost and dew and clouds, condensation. We'll begin that process actually on Monday with Chapter 4. But the coldest times is always when you're most uncomfortable when you go camping is right at dawn. Okay? Yeah. Okay. And in order to get any sort of condensation, whether it's clouds or fog or solid to form from a vapor like frost, that's what that is, cooling down the temperatures is the route to go. And so it's probably some radiation fog shown there.
In terms of the sun's rays, why is this old saying is the darkness before the dawn?
I don't know. I think that would depend on the face of the moon, quite frankly. But
Yeah, it's a metaphor.
it's kind of funny. What?
It's a metaphor. Because usually when people are in trouble, they see
Oh,
the dark.
yeah, it's trying to link to something other than weather.
I was just saying the moon the last 3 nights has been super bright.
Yeah, the moon is very bright. You know, they call the full moons, they give names. Different cultures give names, but this one, January to February, it's like the snow moon. So you're like, well, how appropriate is that?
Isn't it like?
No.
I don't know.
There was a blood moon on my birthday last April.
And blood moon is when?
It's reddish.
It was
Oh.
red, but we also had a lunar eclipse at the same time.
Oh, yeah. Yeah, I guess I have heard
And then there's
the
supposed
blood
to be another
moon.
in October.
Then
there's
there's one in
April.
April, this
Coming
April.
April,
Yeah.
I think there was supposed to be another. They said this
Lunar
one was
eclipse.
different because there was going to be 4 of them. Like, they all had a certain amount of period of time apart, and they were equal periods.
Oh,
of time
yeah, they're
between.
part of a
So it's supposed to be,
cycle.
like, April, October, April, and then late September.
I don't know if you heard what we're talking about. The blood moon is usually when the Earth passes into the sun's rays shining on the full moon, and we call that a lunar eclipse. So at totality, basically, it takes on this eerie sort of redness.
Well,
But
the reason I asked is because a couple years ago, 3 years ago in Job Corps, about October-ish, I happened to be outside and like the moon was like blood red.
yeah, sometimes the moon is really red. Was it low on the horizon?
Yeah, because it looked
Yeah.
bigger.
Yeah, yeah.
The fun time is
The
when you
the
have
the
both
thing,
moon and the
yeah,
sun
the
out
thing
there
about
reflecting
the moon is it can be like the sun, where basically the light is scattered, and we talked about Rayleigh scattering. So the white light from the moon is coming towards us, but we get the short wavelength scattered out, so that it appears red. So basically, the reason the sunsets and sunrises are red is the same reason that the moon is red on the low on the
Quick question, what do
horizon.
they call it when the moon and the sun are out at the same time during the day?
I love that.
I don't know. It's pretty, depending upon the phase. They just call it life.
We've seen that the other
It
year.
happens all the time. Yeah,
It
you
was
just
out
haven't-
through, the moon was out for the entire day.
yeah, it happens.
Isn't
a
the
lot.
reflection of the sun and the moon usually scared by what's in the environment around it?
I don't know, but I need to finish these slides, a few of these slides. It sounds like we're kind of doing astronomy, so I hate to kind
No,
of.
it's not astronomy, it's better, because usually, it's what the contrast of vapors in the air can be different colors from,
Oh, you're talking about like halos and
Yeah.
coronas around the moon?
but they can be different colors and stuff like that.
Yeah.
Yeah.
Moon dogs.
Okay. Okay. Awesome. Get a picture of it, include it in your photojournals. Okay.
Oh,
So.
this is going to tell it to happen right now.
There's different ways to check out what the temperature is, and actually I think I have a slide coming up that, in order to be fair about it and to kind of report our temperature to the world, there are certain criteria. I think it's supposed to be like in the shade, about 6 feet above grass, preferably. But these are measuring devices to get a fix on the temperature. You're familiar with a liquid-filled thermometer. It could be mercury or it could be alcohol. Ours in the lab now are all alcohol, or the red kind. There's also a deal, I'm going to show you a picture, where basically you take 2 pieces of metal that actually will respond to temperatures differently, and they kind of curve depending upon the temperature. I know, isn't that cool? And so in their curving, they actually, I'm going to show you a picture where basically there's that little barrel with paper on it that goes around and it goes up and down. Is that not cool or what? Then there's this one that actually, again, it goes back to metal, but only in one piece of metal, and electricity will conduct that piece of metal differently at different temperatures. Okay, so resistivity and conductivity at different temperatures, and then you just measure how electrons flow. Because I don't know about electrons, or you would imagine at the cold temperature electrons flow more slowly, so they kind of measure that.
Really faster.
Yeah, so these are all liquid-filled
Well, when
thermometers.
electrons start building up, they-
So we talked in this class about the fact that all matter has motion, and actually we're going to revisit that in chapter 4. But down here, this liquid, all matter has motion, you go ahead and heat liquid up and it goes up the thermometer. So there are some fancy thermometers. If you want to snag the high temperature of the day and or snag the low temperature of the day, you can use it with one of these fancy thermometers. You just have to reset it after you look at it. If you kind of focus on it, it kind of makes sense how basically they're segmented to give you the high and low temperature. Liquid thermometers, fancy. I don't know who thinks of these. Okay, so you don't have this picture, but you recognize this picture as the days and the temperature, the maximum temperature, about 2, noon one day, 2 the other. So actually that temperature chart of many days came from this. I just think that is so cool. They use them all the time out in factories.
Looks like a seismograph.
It does look like a seismograph. A seismograph is the same thing. You just wind it up and you just look for the deflection. Yeah. But if you're in charge of monitoring these things, what you want to do is make sure that you rip it off before it rolls back around to the next day.
I worked at a coal factory, we had the flat one. It kept the temperature going.
And it kind of rolled up and caught it, yeah.
Yeah.
Yeah. Sometimes, so you just need to monitor the temperature here, there, other way. So this actually, I'm going to put the word ASOS, and actually that is on your review sheet. What is an ASOS? What's it stands for?
What's it called? AOS?
And it's not edible.
Oh, darn it.
It looks like something.
Automated.
in black.
Hold on. What is it? Automated?
Automated. Surface. observing system. That's the name, but what is it?
Looks like something you.
Automated circuit.
And usually it's a collection of gizmos. What's an ASIC?
It's those things that they put out by the airports. and
Yes,
such.
those things they put out by the airport. And so this is just one piece of that kind of suite of instruments called
Kind of looks
ASICs.
like something you would see in a hospital that helps for people breathe.
Yeah, it does. It does.
Or like it could be it's featured in the next Men in Black movie.
So hidden in there, though, is a gizmo to automatically, thus ASOS, to automatically send the temperature data. So this
What does
one,
it record? Just air temperature variance and stuff like that?
right, to automatically send the temperature. What?
Does it pick up humidity and all of it though? I mean, the actual.
There would be
ASOS
another, she's
part.
asking, does it pick up humidity? There would be another gizmo to pick up humidity. So basically that there's a suite of cute little instruments out there doing their job. Okay? So hidden in there is, looks like a liquid-filled thermometer. Okay? I don't know how that would automatically work. That looks like that takes some manual assistance. But one of the things I want to point out is what color is it painted?
White.
It is painted white. Why wouldn't you paint it black?
It absorbs.
It would absorb heat, exactly. You got it.
Easily lose it in the snow.
Painted white. Yeah, that's true. I was walking in the hallways and I'm like, I told you the joke about why the sky is blue, so when you're mowing the grass, you know when to stop mowing. So with the clouds out here, it's like in the clouds and the snow, I was like, dang, you don't know when to stop snow shoveling. Okay.
You're blinded.
Like,
Let's see, there's 32 Okay. Thank you. So you're probably familiar with a little bit these temperature scales. I'll just go ahead and put them up there. Actually, these are just two. And no, on your test, I'm not going to make you go back and forth between the two temperatures. I know. You can.
It's the math.
Yeah. None of that sort of math anyway. Okay, so, but usually if you're like me, you look at your temperature in Fahrenheit in the morning.
Yeah.
But you're going to see when we get rolling later on in the class with, it won't be math necessarily, but we'll kind of focus on Celsius temperatures. But I do want to, Celsius is metric and Fahrenheit's English. I do want to mention the other metric scale. And actually,
Kelvin?
yes, the Kelvin scale. The term absolute zero is on your review sheet. Okay, so you probably want to pay attention. You probably already know what is absolute zero. It's negative 273.15 Celsius. Yes. What else about absolute zero? What happens? Thermal energy. No motion. Yeah, no motion, no thermal energy. Okay. And like this says, all molecular motion stops. Absence of molecular motion. Exactly. That was my point. But the thing about the Kelvin scale and the Celsius scale, which we're going to be dealing with, they're both metric. I think it says this up here, but 1 unit. I think this is so cool. 1 unit degrees Celsius is equal to 1 unit Kelvin. Is that not fun or what? So basically, they're what we say offset by a number of units, and that number of units is 270. So yes, absolute zero is negative. This one up here is, yep, negative 273.15 degrees Celsius. And the other thing, if you're kind of talking to another scientist, you want to make sure you never say degrees Kelvin, because it's just units of Kelvin for whatever reason. Okay, well, let's stop there, and we'll pick up those last few slides. So nothing due Monday, but we'll just knock this out Monday, and we are going to go ahead and start on Chapter 4, okay? I like Chapter 4. I hope you guys do too.